Recitation problem 1. The drive propeller of a ship starts from rest and accelerates at 2.90 10 to the negative 3 radians per second squared for a time t equal to 2.1 10 to the third seconds. For the next 1.4 10 to the third seconds, the propeller rotates at a constant angular speed. Then it decelerates at 2.3 10 to the negative 3 radians per second squared until it slows without reversing direction to an angular speed of 4.0 radians per second. Question: find the total angular displacement of the propeller. Clearly in this question there are three phases. Phase number 1 accelerating, phase number 2 moving at constant angular velocity, and phase number 3 is decelerating to an angular speed of 4 radians per second. For that reason, let's detail that one phase by phase. Phase 1. Clearly during phase 1, the drive propeller is accelerating at 2.9 10 to the negative 3 radians per second squared. Alpha equals 2.90 10 to the negative 3 radians per second squared. The other information that we have is the time is 2.10 10 to the third second. Since the propeller starts from rest, that means that the initial omega is going to be 0. Let's use the initial angular displacement for all phases to be theta 0 equals 0 for simplicity. Therefore, given the information, the best tool to solve for the angular displacement for phase 1 is theta equals theta 0 plus omega 0 t plus 1/2 alpha t squared. Let's substitute for the known quantities. Theta is going to equal 0 plus the 0 that comes from the omega 0 here plus 1/2. Alpha is given to us to be 2.90 10 to the negative 3. The time is also given to us to be 2.10 10 to the third. Make sure you square this quantity. Solve for the theta. You obtain 6.39 10 to the third radians. Let me call this theta here theta 1 to differentiate it from the others. Okay, now phase 2, it's a constant angular velocity motion. Alright, the known quantities are the time, which is equal to 1.40 10 to the third seconds. Now, in order to solve for the angular displacement, there is only one way to do so, which is the theta is going to equal theta 0 plus omega t. So we need the omega. We know that theta 0 is going to be 0, but we need the omega. Do you know how we get this one? The omega during the second phase is the final omega in the first phase. Therefore, we need to go back to the first phase and solve for the final angular velocity. The final angular velocity equals initial plus alpha t. Very simple and straightforward. Omega 0, we know it's 0, right? Therefore, omega is going to be 0 plus alpha, which is given to us to be 2.90 10 to the negative 3 times the time, which is 2.1 10 to the third. Solving for the omega, we're going to find 6.09 radians per second. Alright, let's use now this omega to be able to solve for the angular displacement for phase 2. This is going to be my theta 2 now. So theta 2 is going to equal 0, because it starts from 0, plus omega that I just solved for now, 6.09, times the time, which is 1.4 10 to the third. Solving for the theta 2, you get 8.53 10 to the third radians. Now let's move on to the final phase, phase 3. It's a decelerated motion. Let's write down the information that is known to us. The initial angular velocity is known because that's the same as the omega during the second phase, which is equal to 6.09 radians per second. The omega final is given to us to equal 4.00 radians per second. The angular deceleration is also given in the question, which is equal negative decelerating 2.3 10 to the negative 3 radians per second squared. Based on these information that we have, the best tool to solve for the angular displacement is the following one: omega final squared equals omega initial squared plus 2 times alpha times the angular displacement, theta minus theta 0. I'm going to start again using the initial to be 0 as far as the angular displacement. The information that we have are omega, omega 0, and alpha, therefore we can solve for the theta. Rearranging this equation, you can easily extract the theta. I'm going to call it theta 3 to be omega squared minus omega 0 squared divided by 2 alpha. Substituting for all these known quantities, you should be able to solve for the angular displacement theta 3. I have been able to obtain theta 3 to equal 4.58 10 to the third radians. Now that we have all three angular displacement for the three phases, we can add them up and find the total displacement. Theta is going to equal theta 1 plus theta 2 plus theta 3. Add all of those, you get theta 1.95 10 to the fourth radians. And that is the total angular displacement.